Hey everyone, back home. I'm here at the Subaru Telescope Observatory base station. We're about to head inside and talk to some real scientists to do some real observation of things like black holes and planets. So let's go.
My name is Michael Latowski.
How did you get here? It seems kind of odd that an Alberta boy would end up in Hawaii running telescopes.
Yeah, it's kind of an odd story, but yeah, I grew up in an area northeast of Edmonton, in a rural area, so the nights were dark and long during the winter, so I was always fascinated by the night sky. But so I was always been interested in astronomy, and when I graduated from high school, I was trying to figure out what I wanted to do, and astronomy just didn't seem like a practical thing. I mean, how am I going to get a job in astronomy? I want to have a job, make some money. So I did the practical thing. I went to NAOJ and took electronics engineering technology and worked in the computer field for a while, repairing computers, installing computer networks and software. And then decided that that wasn't going to be enough, so I decided to go back to university. So I decided to follow my heart this time and go take physics and astronomy and chose the University of Victoria for a few reasons. One is it had a very good astronomy program. Two, the largest telescope in Canada was right nearby there. And three, they had a co-op program in astronomy. So I followed that path, and during the co-op program, I did a number of work terms, and a couple of them were over here at the Joint Astronomy Center in Hilo, specifically for the United Kingdom Infrared Telescope. And so I got a lot of experience there and made some contacts. And then when I was on my final work term at that observatory in Victoria, I saw a posting for a job at this facility, and I was going to be graduating in a few months, so applied and been here ever since and enjoying it.
Wow, very nice. That's an impressive route to get there.
Yeah, it was. I didn't know, where it would lead me, but I took a chance, and it worked out.
What do you think is the coolest thing about your work?
The coolest thing is I get to operate one of the largest, most advanced telescopes on the planet, so that's pretty cool.
So Michael, you operate the telescope for the researchers, and so they want an optical image. What would help the astronomers or the researchers see more clearly the object that they're looking at?
Right, so to see more clearly, you need some way to get rid of the distortion from the atmosphere. And Mauna Kea is a very clear place to begin with because we're in the middle of an ocean, so there's less turbulence. And we're also high enough that most of the local disturbances are below the summit. So, but we do get average seeing where you do need to take out the effects of the atmosphere nonetheless. And one way to do that is with adaptive optics. So as light comes through the atmosphere, it gets distorted, and we can measure that distortion and use a deformable mirror to counteract it. So it applies like the opposite wave pattern, and that cancels out the distortion and you get a clearer image.
Okay, so if I'm understanding this right, you have a flexible mirror on top of these kind of pads, is that right? And the mirror kind of gets pushed and pulled out of shape to compensate for the atmospheric junk?
Yeah, so there's a deformable mirror that's it's on some actuators, and it's a thin mirror, and you can poke the bottom of it and change the shape of the mirror so that you can counteract the distorted waves.
And so then is that your job? Are you the mirror controller?
That is done kind of automatically. It happens very quickly.
Yeah.
So, as the telescope operator, we're responsible for getting things set up, and then once that is running, we make fine-tune adjustments to it to make it work better.
Okay. So do you do that through code? Like, do you have to write new code every time you go up there to compensate for different atmosphere, or do you just kind of pick out of a bucket and say, oh, these are the conditions tonight, we'll use this scenario?
So we have to, there's some parameters that goes into the adaptive optics system. The gain of the feedback that's changing the shape of the mirror, how often it's being sampled, things like that. We can adjust those things. The software is already there. We don't touch the software, but we can adjust some parameters that change the behavior of the adaptive optics system. So if it's, depending on how bad the conditions are, you have to change a few parameters to fine-tune it.
Okay. Have you ever been up for an observations where the conditions were just so awful that you couldn't compensate for them and it was kind of scrubbed?
Yeah, if the conditions are too bad, you can't even use the adaptive optics system. It's not going to have enough signal to noise to do anything.
Okay.
So, yeah, we get all kinds of conditions, but we don't use adaptive optics all the time.
Oh, okay. I thought it was kind of a standard thing. That's cool.
So we use it for some of our infrared instruments.
Okay.
The adaptive optics system is located on the azimuth foci of the telescope, and there's certain instruments at each foci position. So on the azimuth infrared platform are the infrared instruments that can use the adaptive optics system, because that's where it's located.
Okay.
It has to be in the same light path as the instrument.
Right.
So we have instruments also on the Cassegrain focus, on the azimuth optical side, and also the prime focus.
Okay.
So we can, switch up a bunch of instruments up.
Wow.
But only that one foci uses the adaptive optics system.
Okay. Our textbooks make it sound like it's only an optical thing.
No, you can use it for optical or infrared instruments.
Yeah.
But
our textbook is like grade 9, right? So this is, rainbows or spectrums, and so it's very basic. But that's good to know. I didn't realize that you could apply it to outside, and it was more useful to you outside of the optical range.
yeah.
That's cool. Have you, what's the coolest thing that you were a part of observing?
The thing is, when you're observing, they're usually looking at objects that really only appear as, for the most part, point sources on the video screen. So most of the time you don't see anything too interesting, but occasionally they'll want to look at comets, galaxies. Sometimes they have close ones where you can actually see some detail. The most interesting is, I think, a comet that was part of a mid-infrared observation of a comet, and it was breaking up as it got closer to the sun, and you could actually see chunks of it coming off. So each exposure looked different because the chunks were moving, and that was pretty cool.
That is really cool. So all of these images are just still images, right? You just kind of take a picture. It's not like a video, like on Star Trek.
No. Most of the time you're taking long exposures and
Right.
you're tracking the object. But it's just an exposure where you open the shutter, close it after a certain amount of time.
Okay. Thank you.
Yeah.
I just remembered a question from a coworker. So this is Ruby's question. You mentioned dish size, and we were just wondering, what does that mean? An 8-meter, a 10-meter dish? Is that circumference, diameter?
Right, so that's the diameter of the primary mirror.
Okay, it really is the diameter.
Yeah.
Wow, it's
So,
the
yes.
size of my classroom.
8 meters, it's what, 27 feet, something like that. So
That's
you can't
amazing.
really build, it's got like a monolithic mirror, so it's all one piece, the
Mhm.
primary mirror. And you can't really build them larger than 8 meters. They're too fragile, it's hard to support and correct. Because besides adaptive optics, it's also got active optics. So the mirror is supported by 261 actuators, which maintains its shape as it's changing in elevation.
Okay.
And that's happening all the time as well. So you can't really build a mirror bigger than that and still be able to support it properly. So that's why the Keck telescopes are 10 meters. It's a 10-meter telescope, but it's made up of, hexagonal shaped pieces of glass that all fit together to make 10 meters. And the new generation of large telescopes, 30-meter telescope, is going to be made that same way.
Is there something lost? Like you have a complete pane of glass. Is there something lost by going to the hexagonal shapes?
Well, you do have to adjust for those spaces in between the mirrors. So, but usually, if you're taking an exposure, you'll take an exposure of some area of the sky, and then you'll shift it a little bit, take another exposure, or shift a little bit, take another exposure. So, doing that whole shifting process and then adding up all the exposures kind of fills in the blanks as well, and it fills in gaps that the instrument might have also.
Right. Okay.